When we look at measures of variability, these are values that are going to describe the spread, or otherwise known as the dispersion of the data, from a measure of central tendency. So the list of different types of measures of variability, you might have heard of some of them before, right? We have range, interquartile range, variance, standard deviation, and our coefficient of variation. The range is perhaps the easiest one to think about, right? You just take the maximum value and then subtract the minimum value from that, and that gives you the range of your data. So it's literally just the difference between the highest and lowest scores in your data set. It is very quick to calculate, right? Simple subtraction. It is a rough estimate of the spread of the data, and it can change dramatically if you have extreme scores introduced. So if we go back right to that practice slide, right, where we've got a minimum of 1 and a maximum of 25, we could say the range of this data is 24, right? 25 minus 1, 24. However, 25 is an outlier in this distribution. So really, our range should be 9. Right? So that's a good example of how range doesn't really pick up on extreme scores, because if extreme scores are always going to be to the extreme left or the extreme right, either above or below the mean, okay? And the range won't be able to pick up on that because you're solely going off of what is the minimum and what is the maximum. Okay. The next measure of variability is our interquartile range. I will more commonly refer to this as the IQR. And this is the difference between the raw score at the 75th percentile and the 25th percentile. We associate the percentile, 75th and 25th, with quartiles. So if we took our range of data and split it up into 4 different pieces, we would get Q0, which is associated with the 0th percentile. That would be the minimum of the data. And if percentile is like, what the heck is that? We're going to go over those next week. The order of these lectures is always a challenge because you can't introduce one subject without talking about the next one. So, sorry, I was getting emails. Q1 is going to be associated with the 25th percentile, so the lower quarter of the data. Q2 would be the 50th percentile, the exact middle of the data. Q3 is the 75th percentile, or 3/4 of the data. And Q4 is the 100th percentile. Okay. Now, each of these quartile values is associated with a single value that exists at each of these percentiles. Okay. The actual percentile is just referencing what the percentage of the scores are that exist at or below that particular value. So we have a single value at Q3 and a single value at Q1 based on our distribution. We subtract those values and we get the interquartile range, or the middle 50% of our distribution. Okay, so why would we want to use this? It's a good indicator of the spread of the majority of the data, so the middle 50%. If I toggle back to this slide, when we look at the normal curve, you can see that about 68.3% of the data lie between the first, like either +1 or -1 standard deviations from the mean. So we should get most of, or a general idea of what the spread of our data is just by looking at the middle 50%. So it's not influenced by extreme scores because we're not looking at the outskirts of our data set. It's often used with ordinal data. We can use it with highly skewed data as well. So you can use it if obviously any type of calculation is going to be better if you have a normal distribution. But the median and interquartile range are kind of nice ways that you can get around if you've got extreme scores that can't be treated or taken out of your data set. Okay. Variance is another type of measure of variability. This is the average of the squared deviations from the mean. That sentence makes a lot more sense when we actually look at the formula. Just to kind of go into more terminology, deviation just means the distance from the mean. How much does a value deviate, or how much is it different from the mean? Okay. The actual formula, we take the summation, which is what sigma represents, of the difference between some raw score x and the mean of our distribution. So we take that difference, we square it, and then we add up that calculation for every single data point in our set. We then divide that summated value by n. So what we call this process here, and my arrow should be pointing up here, but this top part is called the sum of squares. And basically what this does is it eliminates the influence of negative values, because if you take the square of anything, you should get a positive number. So we're really just interested in the absolute variance or absolute variation from the mean. Doesn't matter if we're going above or below, we just want to know what's the absolute variation. Okay, these are what each of our symbols mean. I discussed those as I was talking, so if you want to read through those again, you can. As an example for you guys to work through, okay, I've given you a set of x values. Okay. In terms of figuring out what our variance is, right, we've got our raw scores, we also need a mean and our sample size. So I've given you those two values here. And then from there, all you would do is take 12 minus the mean. That goes in this box, right? So 12 minus 21 should give you a -9. We would do that for the next set of values, right? 16 minus 21 gives us -5. 18 minus 21, -3. Okay, so you can go through all of those, and then you square each of them, which gives us a series of positive values. Then we add all of these together, divide by 8. Okay, so adding all of them together would give us 292. Dividing by 8 would give us a variance of 36.5. So our data vary from the mean by 36.5 units of whatever we have measured. More commonly used is the standard deviation, which is literally just the square root of the variance. Okay, so you can see the variance formula is here, literally just the square root. So that, when you take the square root of something, your answer can be plus or minus. Right? So that's how when we look at mean and standard deviation, usually it's the mean plus or minus the standard deviation, meaning that you could have a general deviation above the mean or a general deviation below the mean, which are going to be represented in units of what you've measured. So taking the example that we had before, if we calculated our variance as 36.5 and we took the square root of that, we would have a standard deviation of 6.04. Okay. So that means from our mean, when we look at various standard deviations from the mean, those are going to increase above the mean by 6.04, or they will decrease below the mean by 6.04. It is important to note that sample calculations are different from population ones. The formulas I've showed you so far are formulas for populations, just based on the type of symbols that I have used. However, when we use, so those are all population formulas, specifically for the variance and the standard deviation. When we're calculating these different types of variability on samples, we have to account for the fact that we can never sample the entire population. So we implement a thing called degrees of freedom, and this is basically the number of values in a data set that are free to vary. The way that we determine degrees of freedom is different for various types of statistical tests, but for our equations, instead of n being on the bottom, which is our sample size, right, it's going to be n minus 1. Okay, so this just accounts for the fact that you're never going to be able to sample your entire population. So in our variance, we have, instead of n on the bottom, n minus 1. Standard deviation instead of n is n minus 1. Now we can look at the difference between what we would calculate. So using the population formulas in the previous slides, we had 36.5 as our variance and 6.04 as our standard deviation. In our sample calculations, if you go back through and you run all of those and divide by n minus 1 instead of just n, you'll notice that the sample variance is 41.7 and the sample standard deviation is 6.46, meaning we have a greater amount of variability because we are assuming that we haven't collected everyone in our population. It's important you include this error or this degrees of freedom because it accounts for some degree of error that maybe you didn't collect everyone in your population, right? So you'll notice that both the variability in standard deviation as well as variance are larger in these sample calculations than we would see in the population calculations. The last measure of variability is our coefficient of variation. This is a way of normalizing standard deviation, so we would also refer to this as a type of standard score, meaning that it doesn't matter what the units of your dependent variable are. Maybe we're looking at a bunch of different measurements if we look at how many squats, how many push-ups, how many pull-ups a person can do. Each of those is in potentially a different unit. Maybe we looked at how long it took someone to run a mile versus what their 1RM bench press is, right? Those units are very different. However, we can compare them by looking at a coefficient of variation. So again, a way to normalize our standard deviations if they have different units of measurement. So the coefficient of variation, or the COV, is equal to the standard deviation, okay, divided by the mean of some data set. We multiply it by 100, and that gives us a percentage. So the coefficient of variation is a percentage, basically a percentage of the variability that we would see in a data set. So for an example, let's say that we collected VO2 max on people. They have a mean of 60 milliliters of oxygen per kilogram per minute and a standard deviation of plus or minus 6. Okay. We also maybe measured their peak power output, and the mean is 1400 watts with a standard deviation of 200 watts. Right? These units are very, very different. You have some relatively small numbers in one variable, relatively large numbers in another variable. If we do standard deviation divided by the mean, right, for our VO2 max, we would get 10%, and for our peak power output, we would get 14.3%. So this normalizes our units into a percentage or a similar playing field, and then we can determine which variable has more variability based on the value that the percentage assumes. So in this case, the larger the percentage is, the more variability. The lower the percentage is, the less variability. So if we wanted to know which of these values had a greater variability within its data set, we would say peak power output because 14.3 is greater than 10.